I've never seen computer systems architecture and systems optimization being as interesting as it is right now,
Mhm.
right? Because there was a period of researching this. It was just about making microprocessors faster, making a little bit better compilers. But now that we have to specialize, and there's this really exciting application space with machine learning that offers so many opportunities for optimizations, and you have things like FPGAs, and it's getting easier to design chips. It creates all sorts of opportunities for academic research and also for industrial innovation.
You're listening to Gradient Descent, a show about machine learning in the real world, and I'm your host, Lucas Bewald. Luis Ceze is co-founder and CEO of OctoML, founder of the Apache TVM Project, and a professor of computer science at the University of Washington. He is an expert in making machine learning run efficiently on a variety of hardware systems, something that I'm super fascinated by and don't know a lot about. And so I could not be more excited to talk to him today. Why don't we just kind of jump right in? I guess, you're the CEO of OctoML, right? And that's based on the Apache TVM project. I think you also authored. Can you just
Right.
kind of like, for people who don't know, kind of give a description of what that is?
Yeah, sure. And maybe a quick intro. Yeah. So, and I wear two hats. So I'm a CEO of OctoML and also a professor of computer science engineering at the University of Washington. I have many machine learning friends. And on the area, so I mean machine learning systems. So what does that mean? It means building computer systems that make machine learning applications run fast and efficient and do what they're supposed to do in the easiest way possible. And often we use machine learning in making machine learning systems better, which is something that we should touch on at some point. It's an interesting topic. So Apache TVM stands for Tensor Virtual Machine. It started in our research group at the University of Washington about 5 years or so ago. And the context there was the following, 5 years ago, which in machine learning time is just like eons ago, right? So there was already a growing set of machine learning models that people care about and in a faster and faster growing set of those. The fragmentation in the software ecosystem was just starting, the TensorFlow and PyTorch and MXNet, Keras, and so on. And then hardware targets, at that time were mainly CPUs and the beginning of GPUs and a little bit of accelerators back then, right? So, but our observation then was that, well, we have a growing set of models, growing set of hardware targets, and then this fragmentation that's is either you have a software stack that's specific to the hardware that you want to deploy your model to, or they're specific to use cases like computer vision or NLP and so on. We wanted to create a clean abstraction that would free data scientists or machine learning engineers from having to worry about how to get their models deployed, right? So we wanted to have them focus on the statistical properties of the model and then target a clean single pane of glass, clean abstraction across all of the systems and hardware such that you can deploy your model and make the most of the hardware targets as possible, make as much as possible, from the hardware target you're deploying to. As you all know here, and since a lot of machine learning practitioners that listen to this, machine learning code is extremely sensitive to performance, right? So it uses a lot of memory, use a lot of memory bandwidth, which means that use a lot of the ability of moving the data from memory to your compute engine and back, and also use a lot of raw compute power, right? So that's why machine learning hardware is good for machine learning today more and more look like supercomputers of not too long ago, like vector processing and matrix tensor cores and all of these things, right? So a lot of linear algebra. So making the most out of that is really, really hard. I mean, code optimization is already hard. Now, if you're optimizing code for something that's performance sensitive as machine learning, you're talking about a really hard job, right? So anyways, I'm getting there. I know it's a long story, but I hopefully it'll be worth it. So what TVM did, what we started as a research question was that can we automate the process of tuning your machine learning model and the actual code to the hardware targets that you want to deploy it to? Okay. Instead of having to rely on hand tune libraries or relying on a lot of artisan coding to get your model to run fast enough, we wanted to use machine learning to automate that process. And the way that works is TVM runs a bunch of little experiments to build really a profile, a personality of how your hardware behaves, and use that to guide a very large optimization space to tune your model and your code. So the end result from a user point of view is that you take a model as input in TVM, you choose a hardware target, and then what TVM does is it finds just the right way of tuning your model and compiling to a very efficient binary on your hardware target.
And I
Okay?
guess when I think of like,
Does that answer your question what TVM is? I know it's long, but I hope it's useful. Yeah.
yeah, no, it's great. I want to ask some more clarifying questions, I
Yeah.
guess. And I'm not a hardware expert at all. And I guess like what I've observed, trying to make ML models run on various hardware types is that it seems like it's harder and harder to like abstract away the hardware. Like it seems like people are really like kind of building models with specific hardware in mind, sometimes specific memory sizes and
Yeah.
things like that. And I guess my first question
And
is
that's what
like,
we want to change. That's what we want to change. We want to remove that worry from, the model builders, right? We want them to focus on building the best statistical properties possible. And then everything else should be left for engines like TVM and the Octomizer that I can tell you more about later. Yeah.
and so this TVM though, is it actually like a virtual machine where is it doing kind of real time, compiling to the hardware as the model runs?
That's part of the work. Yeah. So TVM by and large is just what we call JITing, just in time compilation.
Hmm.
Right? So the reason the just-in-time compilation is important is because, well, you learn more about the model as you run it, as you evaluate it, right? And then second, you can do measurements of performance and make decisions about how you're going to tune the rest of your compilation,
I see.
right? So yeah, it is a virtual machine in the sense that it offers a clean abstraction. It's not a virtual machine sense in the VMware sense. It's more like a virtual machine in the Java virtual machine sense,
I
which we
see.
can get. It could be a whole different conversation. That gets even closer to my world as a computer systems architect is thinking about those kinds of abstractions, right? But TVM is a virtual machine in the sense that it exposes a well-defined interface for you to express what your model does and get that what we call lower down to the hardware target. Yeah.
Got it. And is this typically for deployment or could it also apply for training time?
Great question. So TVM so far, by and large, it's used as being for inference, right? So you have a model that's being trained. You've often have done quantization too by then, and so on, and then you run it through TVM because that we see that as a strength is that you apply all the optimizations that could change the statistical property of your model, and you validate your model that way, and then whatever we do from there on should be seen as a process that preserves exactly what your model does. We don't want to change anything because we see that it's complementary to all of the other optimization that model builders would apply before then. So then what TVM does is really like a compiler, right?
Hmm.
So it's a compiler plus code generator plus a runtime system, and we specialize everything to your model and the hardware target. We really produce a custom package that is ready to be deployed that has custom everything. It's a custom library of operators for your model, has a custom runtime system for your model, and then wraps it up into a package that you can just go and deploy.
Got it. And are you picturing typically, is this kind of like edge and like kind of low power compute environments, or is this more for like servers and
Yeah,
things like that?
great question. So remember that I was telling you about automating the process and using machine learning to discover what the hardware can do and can do well, and use that to guide the optimization. That's
Hmm.
abstract. That frees us from having to make that choice because essentially, as long as there's no magic involved, obviously, if you have a giant, GPT-3 like model you want to run on a 1 milliwatt power microcontroller, that's just simply not going to work, right? So that's the obvious. But in terms of the actual basic flow of having what we call cost models for the hardware target and use those predicted models to guide how to optimize a model for that specific hardware target. It's essentially the same from teeny microcontrollers all the way to giant, beefy GPUs or accelerators or FPGA based stuff that we support as well. That means that TVM doesn't have any preference of either, right? So we've had use cases both in the open source community, in the research space as well, that we support and we still do it ourselves, all the way into our current, customers at OctoML. We have customers for both edge deployment and cloud deployment because the basic technology is effectively the same. Some of the actual deployment aspects and the plumbing changes a bit. If you're going to deploy it on a tiny device, you might not even have an operating system, for example. So we
Hmm.
support some of that. That's different than a server deployment. But the core aspect of how to make your model run fast on harder targets is essentially the same.
I see. And so I guess like for kind of server level deployments, I feel like, with the exception of TPUs and a few companies, it seems like almost everyone, deploys onto like NVIDIA stuff. So is this sort of like outside of CUDA and cuDNN, or does it translate into something that can then be compiled by CUDA? Like how does that work?
Yeah, this is an excellent question. So first, let's think about just a world with NVIDIA, and then let's just free ourselves from that with the
Okay.
tyranny of that. Okay, which is part of the actually this is part of the goal here too. I love NVIDIA. Many friends there admire what they do, but people should have a choice. So and there's
Totally.
a lot of really good non-NVIDIA hardware. NVIDIA makes great hardware. There's a lot of really great non-NVIDIA hardware there, right? So,
Hmm.
but let's start with NVIDIA. Let's imagine a world that all you care about is deploying on NVIDIA, right?
Hmm.
So NVIDIA has at a very lower level of their compilation stack, they do not expose their what we call the instruction set, right? So that's actually it's kept secret, they don't expose it. You have to program using CUDA, that's the lowest level, right?
Mhm.
So, and there's cuDNN on top. And then
Mhm.
there's also parallel to that, you have TensorRT, for example, which is more of a compiler that you compile a model to the hardware target, right? So TVM can be parallel, but at the same time use those. So here's what I mean, right? So both cuDNN and TensorRT are generally guided and tuned and improved based on models that people care about and moves with where the models are going. There's some fair amount of tuning that moves with where the models go, right?
Mhm.
So whereas TVM again generates fresh code for every fresh model. So that means that in some cases we do better than TensorRT and cuDNN just because we can specialize enough in a fully automatic way to the specific GPU, NVIDIA GPU that you have, and then we generate raw CUDA code that you just compile down, right? So
Mhm.
essentially, you run your models to TVM, produce a ton of CUDA codes, and then you compile that into a deployable binary on that specific NVIDIA GPU. But in the process of doing that, TVM, I mean, we do not take a dogmatic view that you should only use TVM. In some cases, of course, NVIDIA's libraries or NVIDIA's compiler like TensorRT can do better, and we want to be able to use that too. So what TVM does, it does what we call best of all worlds. That in the process of exploring how to compile your model, for parts of your model, say a set of operators, it
Mhm.
sees like, TVM's version and then cuDNN and then TensorRT and picks like, oh, this operator is better to use cuDNN. You just go and put it, and then we link the whole thing together such that what we produce for you is it could be a Franken binary, right? So bits and pieces are, parts of a cuDNN, maybe TensorRT, or, TVM generated code, and produces a package that essentially specializes to your model, including the choice of whether you should or should not use NVIDIA's own software stack. Okay, so did I answer your question on NVIDIA? So this is how we use
Yeah,
it.
yeah,
But
totally.
and by the way, this is just TVM. We should talk about the Octomizer later. The Octomizer, we
Sure.
want to abstract all of that away even further, which is you upload your model, and then you can choose. You have a checkbox of all sorts of hardware: Intel CPUs, AMD CPUs, NVIDIA GPUs, soon AMD GPUs, and then Raspberry Pis and all the stuff. And then you can let it tune for all of those. And in some cases, you might choose to run and use a native stack for you. So you don't even have to think about that. That's really what we want to offer. Like, really not have to worry about it. So
Mhm.
now, okay, TVM, Apache TVM, that's just focused on the open source now, has got quite a bit of traction in both end users and hardware vendors. Like end users, companies like Microsoft, Amazon, Facebook, and so on have used it. Some of them using heavily today. And but now hardware vendors got more and more into the TVM
Mhm.
world. Like ARM built their CPU, GPU, and NPU compiler and software stack on top of TVM. We're working with AMD to build one for AMD GPUs as well, right?
Mhm.
So GPUs and CPUs. Qualcomm has built their software stack with TVM, and we are working with them to further broaden the reach of the hardware that's supported by that. The reason I'm telling you this is that as we enable hardware like AMD GPUs to be used very effectively, via TVM. I think we will start offering users a meaningful choice here. They should go with the hardware to better serve them without having to necessarily choose that based on the software stack, right? So,
Mhm. Can I ask a couple of specific questions?
is that question, or does that make sense or not? Yeah.
No, that
Maybe.
makes total
Good.
sense. But I'm kind of so when we do a lot of work with Qualcomm, and they talk a lot about Onyx, which I think my understanding is that's sort of a translation layer
Yeah.
between
Hmm.
models and places that like hardware that it could deploy on. So how does that connect with TVM?
Yeah. So there's no visuals otherwise I could show you, but there's think of it as there's a stack, right? So the lowest level you have hardware, and then you have what you have or compiler and operating system, and then you have your code generator. So that's where or libraries, right? So
Mhm.
too, and that's where TVM sits. And then on top of that, you have your model framework like TensorFlow, PyTorch, Keras, and MaxNet, and so on.
Uh-huh.
Onyx as a spec is wonderful, right? So essentially, it's a common language for you to describe models.
Uh-huh.
Okay, so and TVM takes as input models written specified in Onyx,
I
but it
see.
also takes native TensorFlow, native PyTorch, native Keras, and MaxNet, and so on. But Onyx is like if you go to the Octomizer service today, you
Uh-huh.
can upload an Onyx model,
Got
right?
it.
And
Got
then
it.
and then in the guts of the Octomizer, you go and call TVM to import a model and do its magic, right? But Onyx, think of Onyx as a language to describe models.
And so do you think that I feel like one of the reasons that I've heard that NVIDIA has been so hard to, displace as sort of the main way people deploy most of their stuff is because the cuDNN library is so effective. Like, do you sort of imagine that as TVM gets more powerful, it opens things up to other hardware
Yeah,
companies?
that's right. Yeah, and okay, so I think Nvidia has been brilliant in offering I mean, they have a really, really good software stack, and they of course have good hardware too. But the
Hmm.
fact they have a usable and broad, and I would say arguably some of the best low level machine learning system software stack there gives them a huge advantage, right? So some other hardware could be just as good in terms of raw processing power, amount of memory, and kinds of architecture and so on. If they don't have a good software stack, they're simply not competitive, right? So, and we definitely see TVM as offering that choice too, right? And again, I don't want to sound like we are going to go and compete with Nvidia. That's not the point. I'm just thinking, just think about this, right? So today, forget machine learning. Let's just think about operating systems, right? So you have Linux. Linux runs in pretty much all the hardware that you care about, right?
Uh-huh.
Sure, you might still choose to run Windows, right? So, but at
Hmm.
least you can, in the same hardware, you can choose to run Windows or Linux, right? So think of it as CVM as offering a choice of what kind of operating system you'd run on your hardware, except that you don't have to choose a proprietary one. And in the machine learning world with NVIDIA, there's essentially no choice today unless you're gonna go and write CUDA code directly, right? So
So I guess like one of the things, and this is probably the part of the show where I ask the dumb questions that my team is going to make fun of me
yeah.
for, but kind of in the back of my head, I feel like I always have this mystery where like a new version of CUDA comes out, and like the models get like way faster with just a
Yeah.
better library. And I think about like what a model does, like a convolution or like a matrix multiplication. It seems so simple to me. It just seems, and that's kind of how it seems like, because I feel like I
Yeah,
come
I
from more of a
know.
math background, and I'm just like, how could you know like many years in to like making a
This is
library like CUDA years, how could there be a 20%
you
speed
know
up on a matrix multiplication? Like, what's
That's a
going
brilliant
on?
question. Yeah, great question, Lucas. And all right, so we should take a whiteboard out, and I'll show it to you. So because then it gets even closer to my world. Let's think about computer architecture for a second, right? So let's say that you are an execution engine, like a processor or a core and a GPU, right? So you have to grab. Let's start with one reason. Like you have to grab data from somewhere in memory, right? So turns out that computers are, memory is organized in ways that depending on where the data is in memory, which actual address physically in your memory it gives you much better performance than others, like by a huge margin, right? So
Mhm.
because depending on how you lay it out the data, you can actually make the most use of the wires between your memory and your processor, between your cache and your actual execution engine in the silicon itself. But
Mhm.
figure out where that goes becomes a combinatorial problem, because not only you have to choose where the data structure go, but also when you have a bunch of nested loops that implements your convolution, you have to choose, like if you have a four deep nested loop, in which order should you execute them? Any order is valid. Which order
Mhm.
should you execute them? And then within those, you might want to traverse, like what size of blocks are you going to traverse that?
Mhm.
So, and all of that is highly dependent on the parameters of your convolution.
Mhm.
I'm just speaking convolution, right? So
Yep.
even just general matrix multiplication, right? So long story short, for any given operator, there's literally potentially billions of ways in which you can compile the same bit by bit equivalent program in terms of output, but
Mhm.
one of them is going to be potentially 1,000 times faster than the slowest one. So picking the right one is hard. Often this is done today by human intuition and some amount of automatic tuning called auto tuning, right? So what's happening in cuDNN as you see your model gets faster is that you have NVIDIA can afford a large number of programmers, right? So a lot of really talented software engineers, they observe where the models are going. There's some models that matters to them. They're going to look at the model, see the parameters of all of the operators, how they're stitched together, and then they're going to start tuning the libraries to make sure that they do better data layouts, they make better loop ordering, they do better tiling of how the data structure works, they choose the direction which they're traversing the data structures and so on. And that's just one type, that's just one operator. But now models, operators talk to other operators, right? So that's why there's
Mhm.
something called operator fusion. If you fuse two operators, for example, like
Mhm.
a matrix multiplication, a convolution to a single operator.
Uh-huh.
So now you can generate code in a way that you can keep data as close to your processing engine as much as possible. So you make much better use of your memory hierarchy. And that's yet another significant performance bump, right? So it might give you a general sense like this is
Totally. That
what
was really
changes in.
helpful. Yeah. So I guess you
Um,
can't actually
yeah.
decompose the problem down into. I was sort of picturing that each step in the compute graph you could optimize it separately, but actually you have to
No, you want
optimize it
them
all
together. In
together.
fact, yeah, if you read the TVM, there were like two, like actually three PhD theses. At the very least, those are the ones that I've been involved in on the core of TVM. And if you read the first paper, it's been around for several years now. One of the key messages there, the highest level, was the following: is that by doing high level graph optimization together with code optimization, that's where a lot of the power comes from. So essentially, say if you choose to fuse two operators in the graph, Now we need to generate really good code for it. So now you're going to go and use our automatic, highly specialized code generator that uses machine learning to do the search for this new operator that fused the two with different parameters. So by combining high level graph optimizations with low level code generation that's specialized to that, you have significant multiplicative optimization opportunities.
Interesting.
Does that give you like yeah? So
No,
that's one
no,
of
that's
the
really helpful. Yeah.
yeah.
I guess do does the new TPU architectures kind of change anything about this optimization, or does it change like what you're doing at all?
Well, it's a different hardware architecture, so you need to go and tune for it as well. But you remember that TPUs are also made of a bunch of transistor functional units and floating point units and vector units, and they have wires, they have memories organized in different in a certain way that you want to make the most of, right? In a sense, a lot of these specialized architectures, what they do, and in fact, we TVM also has an open source CPU like accelerator that's fully open source hardware. You can actually stamp it out in FPGA. Some folks have stamped it out in actual custom silicon. That gives you sort of like a template of how you think about these accelerators, right? So, and they also have parameters. So the different sizes of memories and buffers, what data types you support, how many functional units you have to have the right throughput. And it's all a balance of how you organize your memory, how much of your silicon you're going to devote to compute versus storage, how many wires and how is your interconnection network to move data around is connected. The reason I'm telling you this is that many times the trade-off here is the following: you might make the hardware more complicated to program, harder to program, okay,
Mm-hmm.
but immensely more efficient.
Mm.
But that means that now you need to rely even more on a compiler to make really good code generation and specialize how you're going to compile your code to that specific hardware target.
Right, right.
Because that's a fair trade-off, right? Compilation you do once, it might be complicated,
Uh-huh.
but then if you subsume harder they have to do every time as data is flowing, it's much better to do it ahead of time, right? So
Isn't this a little, I mean, I'm digging deep into my computer science education, but I feel like the story with computer, like the non-deep learning chips, hasn't it been sort of like simpler, kind of like smaller instruction sets and trying to like simplify things? It seems sort of the opposite direction of like adding complexity into the hardware and then relying on the
yeah.
compiler to deal with it.
Yeah. So no, it's a great question. And there's so many. Like this could be a whole other conversation too. But the whole when the risk versus risk debate happened in the computer architecture class that I teach, at grad level, I actually have them have debates, right? So the key aspect there was that by going to a simpler instruction set, you had simpler hardware, so you can actually clock it faster. So
Mm-hmm.
you could have lots of little instructions, but you execute a lot of them per unit of time, so you can make it run faster, right? So it turns out that even complex instruction computers today, like x86 and Intel, they break it down automatically into teeny instructions. It still looks like a RISC computer inside, right? So now, but fast forward to today, what's going on is that there was a huge change in the trends and we've seen performance coming from in different computer architectures, right? So as we get closer and closer to the limits of scaling of transistor technology, what happens is the following: you have a certain number of transistors; they're getting ever smaller and more power efficient. There was a change that transistors are getting smaller, but not necessarily much more power efficient, which means that you can pack more transistors on the chip, but you cannot turn all of them on at the same time.
Mm.
You might be saying, like, why am I telling you this, right? So because that's a whole justification for going more and more specialized and have a bigger chip with
Mm-hmm.
lots of different quote unquote more specialized function units. They're not general, but they're
Mm-hmm.
much more efficient because every time you add generality in the hardware, fundamentally you're adding more switches,
Mm-hmm.
right? So, for example, general purpose CPU that can do anything. There's like a large fraction, more than half of the transistors there are just simply sitting there asking questions: am I doing this or that? If I'm doing this, I do this. And they're like, and then have to make decisions about the data that's flowing through because this is supposed to be general,
Mm-hmm.
right? So the trend that we're seeing now is that, well, we need to make this thing much more efficient. Otherwise, we can't afford the power to run a global infrastructure, or you can't afford the power to run machine learning in your like. You have to squeeze efficiency from somewhere. The way
Mm-hmm.
you squeeze efficiency, you remove all of these transistors just sitting there wondering what they should do with transistors that do only one thing and one thing very, very, very well.
Mm-hmm.
Sure, it makes it more harder to program because now you have to figure out when and how you should use these specialized function units, but they're immensely more efficient in terms of performance per watt and immensely faster than general purpose computers.
So
Did
like
I
what
answer your
was
question or did I make it more complicated? Did I confuse you or
No,
did
this
you
is
help it?
incredible. I feel like I'm
Okay.
finally getting clear answers to questions that have been in my head for a long time. So I'm actually really, really enjoying this. But I guess what should I be imagining as like a specialized instruction? Like I hear like on the M1 laptop, there's like a specialized thing to like play videos, or like what does like a specialized instruction look like? Is it like there's a
Yeah.
convolution
Yeah.
instruction that I
So
could pass through?
for example, it's an 8 by 8 matrix multiply, single
Oh wow.
instruction, right?
Really?
So yeah, that's yeah, you can invoke that. You set up, you put all the data in the right place, and you say 8 by 8 8 by 8 matrix multiply. Boom, it happens.
In like
Or
one in one tick,
yeah,
it does it?
not exactly one text. Like it's one instruction, which means that you give it one command. It could be broken down into multiple cycles, depending on how it's scheduled. But
Uh-huh.
from your programming point of view, there's hardware there. There's essentially an arrangement of your transistors that implements your functional units and your memories organized in such a way. There's something called a systolic array. I don't know if you heard this term before, but
No.
systolic arrays, it's an array of multiply and accumulates. I think it that way, right? So you can just flow data in a specific way that
Uh-huh.
if you just arrange it just right and you flow it through, in one flow, you've done an 8 by 8 GML, right?
Cool.
So, but to do that, you have to arrange all the data in the right place and then click go, right? So
Uh-huh.
not click, issue the instruction go.
Right.
But now to answer your video compression question or video codec, right?
Uh-huh.
So we call it an instruction, but more likely it's essentially a piece of hardware that's just sitting there, knows where to read data from, and what you do is just configure it. You're not giving the program for real is actually in the actual function specific hardware. And all you
Okay.
do in your code is to say, activate that now. Here's the data stream, activate that. And then you have a fixed function hardware that just starts crunching through that and decoding your video, for example, or applying a certain computation. Another thing that people are doing in hardware is activation functions.
Mhm.
Some activation functions is so popular, people use it all the time, that why are you going to break it down into 30, 40 instructions? You can design a piece of hardware that does that and just that, and all you're doing is when you call that activation function, you just activate that piece of hardware,
Wow.
right?
But
So
I mean, wow. So I guess like if it's like sort of laws of physics that are pushing this trend, it seems like you probably expect this trend to continue for a long time, right? And if it does,
oh
like
yeah.
where would it go? Like would there be sort of even more and more complicated instructions possible in the hardware? And wouldn't that sort of make research harder? Like what if you wanted to do a new activation function that wasn't available
Yeah,
in your
it's a
hardware
great
set?
yeah. So that's a really great question, Lucas. So all right, let me try and answer the first big question first, and then we can branch down to these other sub questions about research and how do we continue advancing this. So yeah, so that's the reality right now. It, we're gonna see, we already have a quite a bit of diversity, not just of different hardware chips and hardware parts. Just look at all the AI chip companies out there. Just
Mhm.
look at what's happening to the general purpose processors, like Intel processors getting specialized instructions that are relevant to machine learning and so on. So that's going to continue going, because honestly, there's just no other way to get efficiency, unless, now I'm gonna let me open like a nerdy, not joke, but a nerdy speculation. Unless we can teach atoms to rearrange themselves at the atomic level to go into, like, let's reconfigure where your wires are, and therefore you have your chip doing a new thing.
Isn't that
The
like
only
there's a kind of chip like that, right? Like a FPGA or something. Is that
Yeah,
it?
so but I'm gonna get there. But there's no
Okay.
magic. FPGAs is just, there's a bunch of wires that are there. You're just inserting data to tell you which wires you should use. But the wires are always there. And
Mhm.
just the fact that you have a table that tells you, if I have this bit on, I'm gonna use this wire. If I have this bit on, I'm gonna use the other wire. Just
Mhm.
that causes inefficiencies. So it's always a trade-off. Think of it as a trade-off between how general or hard is your, so there's a generality versus specialized curve. More general, less energy efficient, easier to program.
Uh-huh.
More specialized, right? So more efficient, harder to program, and so on, right? So but then you have FPGAs. Like, how about FPGAs? FPGAs are essentially, they are a very general fabric with a very complicated programming model.
Mhm.
Because FPGAs, what they are, they're a fabric of their bag of wires and little routing tables, and sprinkled some multiply and accumulates, or more and more like activation functions and other popular compute elements that you just sprinkle in an even fabric, and then you just set bits to figure out how you're going to route the data.
Mhm.
So that looks like, the way you program that looks like how you design hardware, and they can be very efficient if you do it right. But fundamentally, they're not going to be more efficient than true fixed function chips. You're never
Mhm.
going to see an FPGA competing with a GPU on the very same task. You see FPGAs competing with things like GPUs and so on, when you can specialize to your application, and even with the efficiency hit of the hardware, you still have a win. Does that
Mhm.
make sense? So for
Totally.
example, let's say if you decide that you want 2-bit data flow for, like, let's say you do quantization to 2 bits here in one layer, 3 bits on the other layer, and 1 bit on the other layer, right? So
Uh-huh.
if it just so happens there's no existing silicon that can do that for you, existing CPU or CPU or GPU that can do that for you,
Hmm.
chances are you're going to be living with an 8-bit data plane, and you're going to ignore some bits there, and then you're going to waste efficiency there, or you're going to do inefficient packing.
Right.
But with an FPGA, you can organize it such that you only activate, though you only route your circuits for to use the 2 bits or 1 bit or 3 bits. In that case, because the data type is more unique,
Hmm.
you can specialize to your model, and then you can do really well with an FPGA.
That makes sense. That
And
makes
now
sense.
on research, answer your question, research. Yeah, so research I think is getting more interesting, honestly. I haven't seen, maybe I'm getting old, and a curmudgeon here, but I feel like, I don't say like curmudgeon, maybe I'm being old and optimistic here, is that I've never seen computer systems architecture and systems optimization being as interesting as it is right now,
Hmm.
right? Because there was a period of researching this, it was just about making microprocessors faster, making a little bit better compilers. But now that we have to specialize, and there's this really exciting application space with machine learning that offers so many opportunities for optimizations, and you have things like FPGAs, and it's getting easier to design chips. It creates all sorts of opportunities for academic research and also for industrial innovation. Hence, we see all of these wonderful new chips and Xilinx with new FPGAs and new FPGA companies and Samba Nova with reconfigurable fabrics and all of these cool hardware targets, right? So
I guess, I mean, this is a little bit, maybe this, well, I guess I'm curious. It seems like ML is becoming a bigger and bigger fraction of data centers, and data centers are becoming a bigger and bigger fraction of, global energy use. Like, do you feel like there's an environmental impact that you can have by making these things run more efficiently?
absolutely, yeah. And we're not the only ones to make that claim. Like, essentially, every time you make an algorithm faster in the same hardware, you're saving energy, you're saving trees, right? So you're reducing resource pressure. So performance optimization is this wonderful thing that you can reap the benefits in so many ways. If you make it faster, you're going to make your users happy. But also, even if it's not latency sensitive, you're going to make your finance folks happier because you're going to spend less on cloud bills. But in the end, you're going to be using less energy, and that really matters, right? So now, what's interesting about environmental impact specifically is that as you pointed out, there's a growing fraction of energy in the world that's devoted to computing, right? So I'm not going to get into cryptocurrencies. Like, we're not going to go there right now. That's a whole separate topic. Think about the energy cost of that. Let's just think about the energy cost of machine learning infrastructure that includes training and deploying models at scale, right? So it's fair to say that in a typical application that uses machine learning today, the majority of the cycles will go to the machine learning computation, right? So even
Mhm.
memory that you have to keep alive with energy, right? So anything that you can do to make the hardware more efficient, to make your model more efficient at the model layer, or making it via compiling and optimizing the model specific hardware is a win, both in terms of user experience and energy efficiencies. And by making more energy efficient, you make it much less environmentally impactful, right? So absolutely. So you should take every opportunity you can to reduce the energy that your models use, especially if it's deployed at scale. Even if it doesn't matter from a user experience point of view, you should do it because that's just the right thing to do, right? So
Can you really separate the like the model compiling and performance and the way that the model's designed? Like, it feels like a lot of the performance improvements in models come from sort of relaxing the constraint that you need to like exactly
yeah,
do the convolution or the matrix. I mean, just for example, like quantization, where
yeah.
you do it in like a ludicrously like small, like level of precision seems to work really well.
No, absolutely. No, and I did not mean to imply that we should only do model compilation. Like, I remember that I said, like, I'm assuming that you're gonna come with your model tuned for for the least amount of computation you possibly use. That's the ideal case. But you're absolutely right that there are optimizations at the model level that actually changes the statistical property of the model that enables new optimization. And we can do that too. But TVM does have growing support for quantization. But what I'm particularly interested in general is how do you put things like TVM in the whole network architecture search loop, right?
Mhm.
So as you make decisions about your model architecture, and as you retrain for different model architectures, and you can make new optimization decisions on the model layer and change the convolution, the data types, and doing all sorts of things like pruning and compression, deep compression, etc. You
Mhm.
know, put a compiler in the loop to like TVM and
Mhm.
measure what's the performance that you're getting as part of your search loop, because then you really get the synergies. You're right that you cannot you can decouple them in principle, and you're
Mhm.
still going to do relatively well. But if you do both of them together, I think you're up for more than the addition of either of them in terms of potential opportunities. That's what TVM did in terms of high level graph and low level optimization. By doing them together, we show that we can do better. And I do think that the same thing. I do think, I have data points that shows that the same thing could happen if you do model building and tuning decisions together with low model compilation and hardware tuning together, right? So
Are there trade-offs between, like, with GCC you can like optimize for memory, or you can optimize for like speed? Is there like a latency memory size trade-off here, or are they both sort of like aligned with each other?
yeah, so that's a great question. Of course, one optimization that definitely impacts memory usage specifically is when you do model compression or if you do quantization, right? So if you go from FP32 to int8, you already have a 4x footprint reduction in your. You go from 32 bits to 8 bits
But
of your
that'll
model
also make
parameters,
it
right? So
run faster, right? So there's no like real trade-off there if the quantization keeps
yeah,
the performance you want, right?
potentially, if you're assuming quantization, that's just like you have the same model architecture, and you just like change the data type and go. But that's, I would say, that's sort of like the easy, lazy quantization. The right way of doing it, in my opinion, is that once you change the data type, you're not given an opportunity to actually go and retrain it, and those some parts of your model become less. I think the right way of doing quantization is not just quantize your data type and forget about it, right? It's actually close the loop and put it on a network architecture search, such that as you change the data type, you actually allow for different types of, and then in that case, I think you're up for significant changes to the model that would make quantization potentially even more effective, right? So
Mhm.
so then, yeah, so you're asking, so, but I did not answer your question. So what's the trade-off between latency and footprint? Well, it could be that, like, it could be that you actually quantize your model, but then you actually make it deeper to actually make up for some accuracy loss, which
Mhm.
might make your model actually potentially slower,
Mhm.
right? But use a lot less memory. So there is that trade-off there too.
I guess like my experience of deploying models, and I'm just an amateur at this, but I love my Raspberry Pis and other,
Yeah, and we
other
have a
cheap
target
hardware.
Raspberry Pis, and we support Raspberry Pis pretty well in TVM. By the way, you should try it out. So
I will definitely try it after this. I did it kind of in the early days of trying to get TensorFlow to run, when even that was a challenge. And I felt like basically with models it was sort of binary, where like either I could fit it in the Pi's memory and it would run, or I couldn't fit in the Pi's memory and it wouldn't run. So it seemed like less about sort of like optimizing, and just like either I'm sort of like stuck or I'm not. Is that like a
well,
common situation, or?
it's hard to say if it's common. Like, often, at least for the models that they get to the point where we pay attention to them and we know that they run now, but they typically don't run, say, the frame rates that you want. You get half
Mhm.
a frame per second, and you can want to show you a path to 20 frames per second, right? So
Uh-huh.
by that time, the model already fits you optimizing per- for performance. But often, this performance optimization comes also with model size reduction. Quantization is another one.
Right.
Let's say if you can just go from FP16 to int8 and it works well, boom, you do that, you probably improve performance, and you also reduce model size, right? But I've seen plenty of cases where the model already runs, and what's hard is actually get to a target latency that would actually enable the model to be useful. That's actually, by and large, what we tend to see is you get your model to run, you hack it enough to go there, but then it's never fast enough, and then you're gonna go and you need to have another 10x ahead of you for it to actually be useful, right? So
Totally. Well, cool. I don't want to not ask you about your company, OctoML. I feel like you're one in a growing line of people that you're
no, it's
talking to. They're professors and they're like starting companies. I mean, what inspired you to to build this company?
Yeah, no, great question. So first of all, it's one of those moments where all the stars are aligned. So TVM had gotten quite a bit. We started a company just about a little under 2 years ago. TVM it had quite a bit of adoption by then already, and we saw more and more hardware vendors is starting to choose TVM as their chosen software stack. And we ran our second conference here in Seattle, and I saw like the room full of people like, oh, there's an opportunity here to make TVM even more broadly, what TVM can do more broadly accessible, right? So, and then the stars I said aligning because I was looking to start another company. Had become full professor a couple of years before then. A lot of the core PhD students in TVM were graduating, and now in started companies like, hey, let's all. And one of our big, a big champions of TVM, Jason Knight, was at Intel at that time, was one of our co-founders. Was also looking to starting something, and then we just like all the stars aligned in form, and I couldn't be. I feel extremely lucky that we had that group of people to ready to start a company, and then and we work really well together. There's a lot of synergy there. But then so that's sort of like the stars aligned part.
Mhm.
In terms of technology, it became really clear to all of us that, look, you have this cross product between model and hardware,
Mhm.
and there's such a huge opportunity to create a clean abstraction there, and at the same time automate a way what's becoming harder and harder about making machine learning truly useful and deployable, right? So honestly, in the ML ops, and I don't love that term, because it means so many things, but going from data to a deployed model, it's clear that the tools to create models got good pretty fast. We have, you know there are a lot of people that can create models today, and good models, a large repository of models to start from.
Mhm.
But after interviewing a bunch of potential customers, realize that, hey, well, people have a lot of difficulties in getting models to be deployed,
Mhm.
precisely because of the software engineering required, and the level of performance requirement and cost requirement, and to make it viable. So we formed OctoML to essentially make TVM even more accessible, or technologies like TVM even more accessible to a broad set of model builders, and also make it part of the flow. Like we have, let me just tell briefly what the Octomizer is. So the Octomizer is a machine learning acceleration platform, right? So it has TVM at its heart, right? So you have a really clean either API, just a couple of calls, upload model, choose, and then download optimized model, right? So then you can choose a harder target, and then you upload a model, you can choose the harder targets that you want, and then the optimizer calls TVM, or also can use Onyx runtime, and we're going to keep adding more. Again, we want to offer the user the abstraction that you upload a model and you get the fastest possible model ready to be deployed on your hardware in a fully automated fashion. You either
Mhm.
get a Python wheel ready to download, or
Mhm.
we're working on gRPC packaging, so you can deploy in the cloud, or cloud functions and so on. And then, so the value add here is all this automation that we provide on top of TVM, and also the fact that, as I mentioned, TVM uses machine learning for machine learning, and we have a data set for a lot of the core hardware targets that the world cares about, just ready to go. So you don't have to go and collect it yourself. So
I would think running OctoML, you'd have real visibility into how the different hardware platforms compare with each other. I'm
yeah.
sure you don't want to offend the hardware partners, but do you sort of have like first pass recommendations for what people should be targeting in different situations?
Yeah, so and that's one of the things that I want the numbers to speak for themselves. So what you can do is, you can, if you come to the Optimizing Facts, we are open for early access, and we actually have some real users already using it regularly. So you upload a model, you can choose all sorts of hard attacks, and then you're gonna get a dashboard saying, here's your model, here's the latency of each one of these hardware targets,
Mhm.
and we can compare TVM with other runtimes like Onyx runtime, for example, and we're going to show you which one you should use, and you can choose based on that. Of course, we're making it that we working hard to improve the interface to enable users to make decisions about costs too. For example, if you might want to get the highest throughput per dollar, for example, right? So I would say that it's fair to say that models vary so much that tell if there's any. It's hard to say up front like this is going to be the best. How do you should run it through the optimizer, get the most efficient version and binder of your model out, and then measure that.
Mhm. Cool. Well, I guess that kind of actually leads me into the two questions that we always end with, which I want to give you kind of time to chew on. And I haven't asked you about a lot of your research that seems super fascinating. But I guess I wanted to ask you, like, what do you think is like a topic in machine learning that doesn't get enough attention? That, like, if you had an extra time to just work on something that you're interested in, maybe you would pick to go deeper on.
Yeah, so honestly, it's getting more and more attention now, but I've always been, and a lot of my research has been on automating systems design with machine learning and for machine learning, right?
Uh huh.
So TVM is one example of using machine learning to enable better model optimization and compilation, but also, doing hardware design and programming FPGAs, for example, is really hard, and machine learning could have a huge place there. So I'd say designing, what I want is really model in and automatic hardware plus software out, ready to be deployed. I think that's one that I'm passionate about, and I think it can have quite a bit of impact, precisely because it you can reap the benefits in so many ways. You get new experiences because you enable new applications, but also making more energy efficient, right? So I think we should actually always look at what is the energy cost of deploying this at scale, if it's going to be deployed at scale. Because in rich countries, you don't think about it, right? You just go pay the energy, even if it's high. But now, if you really actually think about the environmental impact of running this at scale, is something that one should pay attention to.
So
So
this is actually using machine learning to optimize the model,
using machine learning to optimize not just the
the
model, but also
energy
this
usage.
the system. Yes, the model and the system that runs your model, such that you get better behavior out. They can be faster, higher throughput per dollar, but also much lower energy use. And I think it's definitely incredibly exciting and possible to do, right? So that's one of them. Now let's see, one that doesn't get as much attention, but now it's getting more attention, that's dear to my heart that we're not touching too, is the role of machine learning in molecular biology.
Oh,
right?
yeah, me too. I totally agree.
So I, as part of my research personality, like I for the past 6 years or so, I've been heavily involved in an effort to design, systems for using DNA molecules for data storage and for simple forms of computation. Some of it is actually related to machine learning. For example, we recently demonstrated the ability of doing similarity search directly as a chemical reaction. And what's cool about
Wow.
that is that not only it's cool, like definitely pushing as a new device technology alternative
Yeah.
that's very viable and has been time tested by nature, right? But it
Time
can be
tested for sure.
yeah, it can be extremely energy efficient,
Uh-huh.
and and fundamentally the design of molecular systems is so complex that I cannot imagine any other way to design them than using machine learning to actually design those molecules. And we do it all the time. Like we had a paper that you might find cool late last year. It was in Nature Communications called Porcupine. And we use
Uh-huh.
machine learning to design DNA molecules in such a way that they look so different to a DNA sequencer. They're not going to be natural DNA, but we can use this to tag things. So we
Mhm.
we design these molecules. You can go and tag art or tag clothes and so on. So you take a quick sample, you run through a sequencer, and you can authenticate that based on these molecular traces. But that was made possible because of machine learning in designing the molecule, in actually interpreting the signal out of the DNA sequencer and so on. And I feel this space it's not fair to say it's not getting enough attention. I think it's getting more and more now, precisely because of the pandemic and all of the other reasons why molecular biology matters, right? But I find it incredibly exciting, and it's a lot of the high level motivation for things that I do, both in research and in industry, is enabling use cases like that. Things that require so much computation that wouldn't be possible before without a very efficient, very fast system, right? So
Mhm. Cool. And I guess the question we always end with, which you've touched on a lot in this conversation, is really what you see like the big challenges are today of getting machine learning working in the real world. Like, maybe when you talk to your customers and they sort of optimize their models, like what are the other challenges that they run into when they're trying to get their optimized model just like deployed and working for some end use case?
yeah, so well, of course, I'm devoting a good chunk of my life into the deployment, automating the engineering involving deployment, but
Totally.
I don't want to sound too self-serving to say that's the biggest problem. I think that's a huge problem. It's a huge impediment in terms of skill set, because it requires people that know about software engineering, about low-level system software, and know about machine learning. So that's super hard. So that's one, definitely
Hmm.
getting your model ready for deployment. But then there's other ones, which is just making sure that your model is behaving the way it's expected post-deployment,
Hmm.
like observability, right? So making sure that there's not unexpected inputs that make your model misbehave, have fail-safe behavior, and so on. I think that's one that is no news probably to this community, that some applications require, either because it's the right thing to do when a model is making decisions that are super important, you want to understand how they're done and
Hmm.
making sure that they actually hold in unexpected inputs, right? So I think that's one of the harder ones, because like any engineer, that's thinking about the whole system, you want to think about the weakest link in the system failure, and I worry that if you don't do something proactively, the weakest link in these systems are going to start being the models that you can't really reason them in a principled way.
Yeah. Awesome. Well, thanks for your time. This is a lot of fun.
Of course, thank you, Lucas. This
Really
was
appreciate it.
awesome. Yeah, so
Yeah.
I enjoyed it immensely. Thank you.
If you're enjoying Gradient Descent, I'd really love for you to check out Fully Connected, which is an inclusive machine learning community that we're building to let everyone know about all the stuff going on in ML and all the new research coming out. If you go to wmb.ai/FC, you can see all the different stuff that we do, including Gradient Descent, but also salons where we talk about new research and folks share insights, AMAs where you can directly connect with members of our community, and a Slack channel where you can get answers to everything from very basic questions about ML to bug reports on weights and biases to how to hire an ML team. We're looking forward to meeting you.